All right, this is section 3.7, optimization problems. We're going to dive straight in. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with a maximum volume? Well, I know that the base is going to be the same, so it's x by x. And then I'm going to have a height. I'm going to call it h. I know the surface area has to be the base, which is x by x, so x squared, and four sides that'll all be x by h. And I know that I want that to equal 108 square inches. All right, that's what I know. I also want to find a volume. So the volume formula for a box is length times width times height, x squared h. Problem here is that I have two different variables in my functions. So what I need to do is take the function that I know the most about and solve for one of the variables. I'm going to solve for h. So I'm going to subtract that x squared over, making it 4xh equals 108 minus x squared. And then I'm going to divide everything by 4x, telling me that h equals, let's see, 108 divided by 4, let's just leave that, 108 minus x squared over 4x. Now I'm going to take that and plug it into my other function, because this is the function that I am trying to find a maximum of, maximum volume. To find a maximum, I need the derivative. To find a derivative, it's much easier if I only have one variable. So I'm going to plug in that h. So x squared times 108 minus x squared over 4x. And now I can simplify that a little bit, because one of these x's cancels here. So I have 108x minus x cubed over 4. Let's make that just a little nicer. 108 over 4 is 27x minus 1/4 x cubed. Now I can find the derivative, v prime. It's 27 minus 3/4 x squared. Now to find the maximum, I need my critical number, which is set this equal to 0 and solve for x. Well, I would add that 3/4 x over, or x squared, multiply by 4/3, which makes 36. Oops, I changed that to a cube. There we go. Square root, and I get x equals positive or negative 6. Now I always need to double check to make sure that this number is a maximum. I got negative 6 and 6. Plug in a number smaller than negative 6 to my volume formula. Let's say negative 7. I'm going to get a negative. Something between negative 6 and 6, I'm going to get a positive. And something bigger than 6, I'm going to get a negative again. Well, at negative 6, I have a minimum because I go from decreasing to increasing. But at positive 6, I have a maximum because I go increasing to decreasing. So the maximum volume is going to have that x side as being 6 inches. Now I still need to figure out what that height is going to be. For that height, I'll go back right here. 108 minus 6 squared over 4 times 6. Sounds like a calculator problem to me. 108 minus 6 squared over 4 times 6. I want to make a box where that base is 6 inches by 6 inches and the height is 3 inches. Some guidelines for these applied minimum and maximum problems. Identify all given quantities and all quantities that need to be determined. If possible, make a sketch. A picture really does help. Write a primary equation for the quantity that is to be maximized or minimized. That was our volume formula. Step 3, reduce the primary equation to one having a single independent variable. This may involve the use of a secondary equation relating the independent variables of the primary equation. That was what we did with the surface area problem, so that we could solve for h and plug that into our volume. Determine the feasible domain. We didn't even have to consider negative 6 on that last problem because I can't have a box with a side length of negative 6. And determine the desired maximum or minimum value by the calculus, which is what we did. We took the derivative and found our maximum. Let's try another one. We're going to figure out which point or points on the graph of 4 minus x squared are closest to the point 0, 2. So to do that, we need to know the distance formula. Well, distance is the square root of x minus x1, which will be 0, squared, plus y minus y1, which will be 2, squared. This is what we want to minimize. So that's what I'm going to want to take the derivative of. But I don't want to have x's and y's in there. I want to use this function so that I don't have to worry about y's anymore. So my distance is the square root of, that just becomes x squared, plus 4 minus x squared minus 2, all squared. I'm going to simplify that function a little bit before I take the derivative. I get x squared plus negative x squared plus 2, all squared. X squared plus x to the 4th power minus 4x squared plus 4. So my original problem is going to be square root of x to the 4th power minus 3x squared plus 4. Now, to find the minimum value, I'm going to take the derivative, which is 1 over 2 square root of all that, times the derivative of the inside, which is 4x cubed minus 6x. Let's simplify this a little more. I'm actually going to divide that 2 out, so I get 2x cubed minus 3x. And in the bottom, I'm going to factor this x squared. Just kidding, that doesn't factor. X to the 4th power minus 3x squared plus 4. So now we need to know where that is equal to 0 or does not exist. The bottom, since it doesn't factor, quadratic formula wouldn't really work. There's nowhere that the bottom is 0. So we just have to worry about the top. I'm going to take an x out. I get 2x squared minus 3. We get x equals 0, and x equals plus or minus the square root of 3 over 2. All right, look at my number line. Negative square root of 3 over 2, 0. Positive square root of 3 over 2. Let's see, something smaller than negative square root of 3 over 2. Negative 2 works. I get a negative over a positive, so that's a negative. Something between negative square root of 3 over 2 and 0. I'm going to pick a 1. I get a positive over a positive. Something between 0 and square root of 3 over 2. I get a negative. And over here, I'll get a positive. Well, here I have two minimums, decreasing to increasing, decreasing to increasing. I have minimums at negative square root of 3 over 2 and positive square root of 3 over 2. Question asked what two coordinates are closest. If I plug in negative square root of 3 over 2 to that original y equals function, I get 4 minus square root of 3 over 2, which is 5 over 2. And if I plug in positive square root of 3 over 2, I also get 5 over 2. Those are the 2 points that are closest to 0, 2. Next up, we have a rectangular page, which is to contain 24 square inches of print. The margins at the top and bottom are to be 1.5 inches, and the margins on the left and right are to be 1 inch. We're going to determine what the dimensions of the page should be so that the least amount of paper is used. Well, first off, we know that x times y has to be 24. X times y equals 24. I know that. I can find the area formula for the whole page, which is going to be x plus 1.5 plus 1.5, so plus 3, times y plus 1 plus 1, so y plus 2. That's the total area of the page, and I want to minimize that. Well, now I have enough information. I can rewrite my area formula in terms of one variable using this top function. And you get to choose, do you want to do x or y? I personally am going to choose to solve for x. X equals 24 over y. So then I plug that in down here. 24 over y plus 3 times y plus 2 equals my area. To make my life easier, I'm actually going to FOIL that out, and I'm going to move the a to the front. 24 over y times y is 24. Plus 48 over y plus 3y plus 6. So my area formula before I actually do any calculus is going to be 48y to the negative first power plus 3y plus 30. Now I take my derivative. A prime is equal to negative 48 over y squared plus 3. Set that equal to 0. Let's add the 48 over y squared over. Multiply the y squared over. Divide by 3. And square root y is either positive or negative 4. Now my paper cannot be negative 4 inches wide, so I know negative 4 is definitely not the answer. I'm not even going to consider it. I'm going to make my number line with just a 4 on it. If I plug in something smaller than 4, let's say a 2, into my derivative, I get a negative. If I plug in something bigger than 4, I'm going to get a positive. So that means my minimum is at 4. So my minimum amount of paper is when y is 4 inches and x is, way back up here, 6 inches. That's actually not the question. The question asks for the dimensions of the page. This is the dimensions of the printed part. The dimensions of the actual page are going to be y plus 2, so 6 inches, and x plus 3, so 9 inches. The whole page is going to be 6 inches by 9 inches. All right, so now we have 2 posts. One's 12 feet high and the other's 28 feet high, and they're standing 30 feet apart. They're to be stayed, so stabilized, by 2 wires attached to a single stake running from ground level to the top of each post. We want to place the stakes so that we use the least amount of wire. So we have a picture here. A 28-foot post, a 12-foot post. This is going to be x, this is going to be 30 minus x, because they're 30 feet apart. I want y plus z to be the smallest it can possibly be. So we're going to use this w equals y plus z. That is what we are trying to minimize. Well, what else do we know about this? We know the Pythagorean theorem is true. X squared plus 12 squared equals y squared. And we know that same thing is true for the other triangle. 30 minus x squared plus 28 squared equals z squared. And it looks to me like I could just square root both sides. And then I can plug those in my formulas only using x. And I can determine how far from each post my stake needs to be. So w is actually going to equal the square root of x squared plus 144, because that's a 12 squared, plus the square root of, let's simplify that a little bit. This actually becomes 900 minus 60x plus x squared. And 28 squared is 784. So let's make that x squared minus 60x plus 1,684. There we go. Now we can find our derivative. It's not a super pretty derivative, but we can find it. I get 1 over 2 square root of x squared plus 144 times the derivative of the inside, which is 2x, plus 1 over 2 square root of all this times the derivative of the inside, which is x squared, or 2x minus 60. Now personally, to do this problem, when I set this equal to 0, I'm going to subtract one of these to the other side, and then I'm going to cross multiply. That's what I would do. Or I'd square everything. Let's start by subtracting this one to the other side. I'm actually going to cancel the 2's. So it makes it negative x over square root of x squared plus 144. I'm going to cancel 2 over here, so I get x minus 30 over the square root of x squared minus 60x plus 1684. Now to make everything in my life easier, I'm going to square both sides. Now I have x squared over x squared plus 144 equals x squared minus 60x plus 900 over the square root of x squared minus 60x plus 1684. Nope, no more square root. My bad. There we go. Now I'm going to cross multiply. X squared times all this makes x to the 4th power minus 60x cubed plus 1,684x squared. Multiply this side out. I get x to the 4th power minus 60x cubed plus 900x squared plus 144x squared. I'm going to go on another line here. Minus 8,640x plus 129600. I'm going to get everything over to the left side. Subtract my x to the 4th power over. Boom, it is gone. Move my x cubes over. Boom, those are gone also. Move my x's over. I get 640x squared. Move my x's. I get positive 8640x. And move that 129,600. So that way it's equal to 0. Now I'm just going to type this in my calculator and use quadratic formula. My answers are possibly x equals 9 and x equals negative 22.5. Well, I know that x can't be a negative because it is a distance. So my answer better be 9. Check in a number line. Well, on the left side of 9, my original derivative is negative. And on the right side of 9, my original derivative is positive. So 9 is my minimum. So my answer is 9 feet from the left pole, which means 30 minus 9, it is 21 feet from the right pole. There's the most efficient way to go about it. And finally, 4 feet of wires to be used to form a square and a circle. I want to know how much wire I should use for the square and how much I should use for the circle to enclose the maximum total area. Well, I know that to enclose a square and a circle, I need to add together their perimeters. The perimeter of a square is 4x. Perimeter of a circle, or circumference, is 2 pi r. And that's going to equal 4. I also want the maximum area. Well, the total area will be the area of the square, which is x squared, plus the area of a circle, which is pi r squared. That's what I want to maximize. Now we can follow those same steps. We're either going to choose to solve for x or choose to solve for r. I personally am going to solve for x because I think it'll be a little easier. Because we just subtract the 2 pi r over and then divide by 4. So I get 4 minus 2 pi r over 4, or 1 minus 1/2 times pi times r. Plug that in here. 1 minus 1/2 pi r squared plus pi r squared. To make my life a little easier, we're going to multiply that out and then combine these. We end up with my area is 1 minus pi r plus 1/4 pi squared r squared plus pi r squared. Since this is what we're trying to maximize, we are going to now take the derivative. Well, derivative of 1 is 0. Derivative of pi r is just going to be minus pi. Derivative of this part is going to be 1/2 pi squared r. And here we'll get plus 2 pi r. I need to set this equal to 0. Let's keep this minus pi over here. Let's factor out an r so that I can get the r by itself. There we go. Add the pi over. And then I can quickly get r by itself by dividing pi divided by 1/2 pi squared plus 2 pi is going to be our r. We'll turn that into a decimal. It is about 0.280. Double check here. Into my derivative, if I plug in something smaller than 0.28, I am going to get a positive. Plug in something bigger than 0.28, I get a negative. So 0.28 is going to be my maximum. So my circle will have a radius of 0.28, which means the amount of wire to enclose the circle is 2 pi times 0.28, which is about 1.760 feet of my wire. And to do the square, I take 4 minus that. I'm going to use about 2.240 feet of wire for my square.